Good afternoon. Can everyone hear me? My name is Klieber, and in this session, Professor Claire Goues and myself will be talking about automated code repair. So as you've heard in the previous talk, static analysis can be used to help find bugs, but often the volume of alerts is overwhelming to developers. However, there are many classes of bugs that have a common pattern of repair, which lays the foundation for techniques for automated repair. So, why would you want to do repair at the source code level as opposed to using a compiler pass? That is, of modifying the compiler to repair the code as you're doing the compilation, which is generally an easier process than repair at the source code level. So one answer, and in fact I think the most compelling answer, is that repair at the source code level can be manually audited and, if necessary, tweaked for performance. Whereas with a compiler pass, you must rely on the tool, you must trust the tool, and you cannot optimize any of the changes that it makes. Additionally, repairing the source code is a one-time change, whereas with a compiler pass, you're tied to that particular build process. In the first half of this talk, I will talk about repairing invalid memory accesses, including repairing bounds checks that are faulty due to integer overflows, inserting missing bounds checks, and repairing reads of stale sensitive data. Then Professor Goues will discuss the use of separation logic for automated reasoning about the semantic effects of program fragments. This addresses memory leaks, resource leaks, and null pointer dereferences. So we have developed techniques for automated repair of integer overflows that lead to memory corruption. Integers in C are represented by a fixed number of bits n. Overflow occurs when the results of an arithmetic operation cannot fit in the number of bits available. With unsigned integers, this leads to modular arithmetic in which only the least significant n bits are kept. So, how does integer overflow lead to memory corruption? There are two main ways. In the first, an arithmetic overflow occurs in a bounds check for an array. Then, a bounds check that should have failed can instead succeed, allowing an invalid memory access to occur. The second way is if integer overflow occurs in the calculation of how much memory to allocate. In that case, too little memory will be allocated, which sets the stage for a later out-of-bounds memory access. Some examples of integer overflow leading to buffer overflow include the Android stage fright vulnerabilities from 2015, which allowed remote code execution, a bug in Ruby's standard library that allowed unauthorized disclosure of information, and a bug in Rust's standard library discovered just last month, which allowed memory corruption. The fix is to repair inequality comparisons that involve array indices or bounds to emulate normal, non-overflowing arithmetic. This includes malloc, which internally compares the size of the requested memory to the largest unallocated chunk. So here we see a fragment that attempts to copy n bytes of data from a source array to a destination array, starting at index start of the destination. So before the mem copy, the program does a bounds check to make sure that the data will fit in the destination array. However, an integer overflow can occur in that bounds check. So how we fix that is to replace the overflowing arithmetic with equal to a function that we insert called uadd, which does saturation arithmetic. With saturation arithmetic, if the arithmetic would overflow, we instead return the largest representable value, size max. And size max will always be greater than the size of any allocated array, so the bounds check will behave as expected. So we have implemented this technique and tested it on OpenSSL and Jasper. We use Kint to detect whether an arithmetic operation can potentially overflow, and then we narrow down those overflows to only those that are sensitive, that is, those that involve array indices or bounds. So in OpenSSL, our technique was able to repair 77% of sensitive overflows, and in Jasper, it was able to repair 52%. Now, some of these repairs are actually false positives, but other ones are actually correspond to known vulnerabilities in the tools. So our ultimate goal is to be able to repair a program to enable a proof of memory safety. In order to do this, we need to ensure that whenever the result of pointer arithmetic is used to access memory, that the result of the pointer arithmetic is still within the bounds of the original allocated memory region. So here we see a fragment of code on the slide. The first thing it does is to allocate some memory. It allocates an array of n elements, and then it loops through up to the first k elements. However, you might see that the code never checks whether k is greater than the length of the array. So in order to fix that, we insert a bounds check immediately before the potentially invalid memory access to check to ensure that it is within the bounds of the array. For each memory access, we first try to prove that it's within bounds. If we can't prove that, then we attempt to insert a bounds check using the pre-existing program variables, as we did on the previous slide. If that doesn't work, we next try a so-called fat pointer approach, where we modify the function signatures and/or struct definitions to include missing information that would enable us to insert a bounds check. And if that doesn't work, our last resort is to use a global lookup table to store the array bounds information, which is much slower than the other approaches, but it works in basically all cases. And of course, we hoist the bounds check outside of a loop where possible to increase performance. So in the past, fat pointers were disfavored because of binary incompatibility if you used a third-party library that was only available in binary form. However, we will overcome this limitation by using Pharos. Pharos is a framework for static binary analysis and transformation developed here at SCI. So it actually turns out that even if we get all of the bounds checks right, there are still some types of vulnerabilities that can result, even from reads that are within the bounds of the array. So here's an example of that. Let's consider a web server that receives requests from different clients. So after the first request that it receives, it has a buffer with that request that is tainted with sensitive data, in this case, a password. Then suppose the server receives a second request from a different client. If that request is smaller, then it only partially overwrites the buffer, leaving still sensitive data in the remainder of the buffer. So when the server replies to the second client, it should not include any sensitive information supplied by the first client. So the bound for reading should be in this case, the most recently written position corresponding to the end of that request, because after that point, there's still potentially sensitive data. So we have implemented a technique to address this problem using a dynamic analysis, and we've implemented it for both C and Java. So our implementations are able to detect and stop the heartbleed vulnerability in OpenSSL in C, as well as the jet leak vulnerability in Jetty. Jetty is a web server written in Java that had basically this exact type of problem. We have also ran our tool on GNU core utils, doing the dynamic analysis using the test suite supplied with core utils, and we got a false positive rate of about 2 false positives per 10,000 lines of code, which is pretty reasonable considering this is still very preliminary research. And that's the end of my section, and now I will turn it over to Professor Goues.
Thanks, Will. Is the mic picking me up? Okay, good. If you want to talk to me, you can call me Claire. Will is very polite to introduce me so formally. But that name is pronounced Goues, so there's your fun fact for the day. So I think a key theme of this work overall, both mine and Will's, is that many broad classes of bugs share properties that we can exploit. So even though projects and particulars and coding styles may vary, mistakes have a lot of useful commonalities that we can take advantage of to help fix them automatically. So hopefully you saw that in the integral vulnerabilities work that Will was describing. And that's also a theme that underlies some of the work that I'll be describing now, that looks at how we can fix certain bugs by extending static analyses that could previously only find them. And this is important because although testing is a really common QA technique in practice, it's not suitable for finding broad classes of bugs. So I want to give you one example of a bug that testing totally misses. This is taken from an open source project called ErrorProne. It's an open source project released and maintained by Google. I'm not picking on the Google engineers in any way. They actually did all the right things, which is what I think makes this example so compelling. There's a bug in this code, or there was. You don't have to think too hard about what it does. The point is just that the variable method on the second or third line of this patch, it can be null, which means that the call and the return statement on the last line of meaningful code could result in a null pointer exception. A developer found this. They did all the right things. They fixed it. They added a test to guard against the regression. And they fixed it by inserting a call to this project-specific handler that checks if a condition is true or false, and if it's false, throws an API-specific exception to be handled elsewhere. So all the right things happened. But the reason this kind of bug keeps me up at night, like so many bugs, is that about 50 lines later in the exact same switch statement, someone made the exact same mistake, which is to say that bugs are patterned. And the thing with this bug is that it's the exact same issue. It took them another 18 months to find it. So this, to me, it's a little distressing, right? Because we had all the pieces there, but a single test, even a very good one, can really only find one bug at a time because that's the nature of concrete execution. Fortunately, although testing is very common, of course, we've been talking all afternoon about static analysis tools, they tend to be good at finding these kinds of bugs. So not just null pointer exceptions that are patterned, but also other bugs that are difficult to test for, like resource or memory leaks, which are the kinds of bugs I'll be telling you about right now. So our key insight here is that there exist scalable static reasoning approaches that can be extended if we adapt the reasoning and apply it in a slightly different way to find patches for bugs that it could previously only find. So I'll show you sort of an idea of the use case here in a second. We're building on the Infer Static Analyzer, which is a tool released by Facebook. It's built on separation logic. We're focusing on 3 classes of bugs that Infer can handle. There are many more than 3. You can see on the right, there's a long list. I don't expect you to read it. We focused on the first 3 because they're particularly well understood sort of components of the analysis, but there's no reason anything I'm telling you about couldn't extend to the other kinds of bugs as well. And what we're doing here is adapting the underlying reasoning, which is based on separation logic and the frame rule, which describes and reasons about what the code does, to search over the rest of the program to find appropriate patch code for bugs that it could find. So vision here, which I think Will alluded to at the beginning, is of an end-to-end push-button integration of static analysis, bug finding, and fixing tools. So the current use case looks something like this. We have a developer who's developing, and she'll push a commit to something, some repository, either internal to your organization or external if she's working open source. And a lot of organizations now, not just Facebook, are using on commit these static analysis tools to help find problems as soon as possible. So this can allow an automatic analysis of these commits, maybe in a continuous integration context. It can find a bug, reports it to the developer, who now needs to think about it, debug, and find a fix. The vision here is that once this bug is found, instead, we'll call a tool, maybe something like Footpatch, the tool I'm describing, or maybe other tools built on other static analysis techniques, to generate an automatic bug fix that can then be validated by the developer much more quickly than if she had to develop her own fix on her own. And if you imagine a more time-critical or real-time context, maybe it's 2 o'clock in the morning, and we have found a security critical vulnerability, and we might have enough confidence because of the underlying static reasoning to deploy the bug fix for a few hours until the developer wakes up in the morning and can review it, and therefore enhance the reliability and security of our systems. So I want to talk a little bit, I'll give you a bit of insight as to how we do this with Infer, but hopefully you can see how the principles might apply broadly. So the basic idea behind separation logic is that it abstracts code to reason about certain properties that it cares about or the kinds of bugs that it's looking for. So in this example, you can see that it's abstracting only file handles, and it's tracking whether or not those file handles can be leaked. So in this C code, the file pointer is open before the call to if getS, et cetera, equals null. And then at this return statement, the file pointer is still open. And so if this function returns, it'll be dead. This is a resource leak, and Infer will report it. And the idea here is that we would step in at this point and provide a patch. I picked a different language, which is to say this is in C and the other examples in Java, mostly so I would remember to tell you that this approach actually works off the shelf on a variety of different programming languages because it's all built on top of an internal representation to which different front ends have been built. So this can apply to a bunch of different projects offhand. That said, the goal here is now to find a patch that would close that file pointer before the return, right? And you might say, okay, well, why is that hard? If you're a C programmer or a programmer in an imperative language, if you've ever interacted with a file handle before, you say, Claire, just call close. Like, this isn't like rocket science, right? But it's hard because developers often don't just call close when they're managing resources. And we see this again and again in the projects that we look at, that developers often create custom handling code or custom resource management code to do extra things like logging, for example, when they're manipulating resources. So what we really want to do is not just insert a generic call to close, but figure out what the developer would have done and make use of her own protocol in fixing the patches by searching semantically over the code base for the code that closes a resource in the way that the developer would. And so this gives an example of a call to a closed resource that does the appropriate thing on the reader object, but does something else too that the developer cares about. And we see this all over the place. In the sort of context of this amount of time, I can't explain all of separation logic-based static analysis to you, although it is very cool, and I wish I could. But I can maybe give you a little intuition. The analysis that's being used here scales basically because it ignores part of a program state that a piece of code can't possibly impact. So this is effectively what the core underlying inference rule, which is what this is, in separation logic does. It's called the frame rule, and it says, effectively, the statement that I am reasoning about does a thing. It closes a file without affecting anything else in the program. So what it ends up doing is pulling out all of the program state, heap state in particular for these kinds of bugs, and figuring out what can be ignored over the course of reasoning about the entire program. And this makes the analysis much more scalable. This is how it finds bugs in a scalable way over real programs. Our insight here is that we can do the same reasoning, but asking a slightly different question. So if you look at this frame rule, the question is asking is, what does this statement affect and what does it not affect? We say, can we find a statement that affects only the thing we care about? Which is to say, whether a file handle is closed. Because if we can find something that allows that inference rule to discharge, it means that that piece of code does exactly what we want it to do. In this case, fix a file leak, or eliminate the possibility of a null pointer exception, or fix a memory leak, for example. So this gives you an example of a kind of query that we can issue to look for code that closes a file resource by adapting and twisting very slightly the analysis that was previously only looking for code that didn't close a resource before it returned. So just to illustrate, quickly, if we knew that we have this bug I showed you before, we're failing to close a file pointer, we're going to look somewhere else in the code for something that causes the inference rule to discharge, which is to say, it leads an open file pointer to be closed, and then with magic that I'm hand-waving, translate that back into syntax and insert a patch that does exactly the right thing. This is a slightly boring patch because it's just a call to close, which I told you earlier was boring, but I'm showing it to you because it's actually a real patch that we submitted as a pull request on GitHub and that the project maintainers accepted, And so we were excited about it. And so that's why I picked a boring example instead of a slightly more complicated one. I'm a little disinclined to walk through this entire table. But this table shows you some results that we have on real programs in both C and Java. The bolded projects are those in which we found bugs that had previously not been found by the developers. On a number of these programs, we have issued pull requests and had developers accept them and thank us. The bugs column shows the number of bugs of that particular type that the analysis found. That's from Infer, that has nothing to do with us. The fixes column shows how many of those bugs we could repair. And the time column shows how long the whole thing takes. So not the fixing component, but the process of analyzing the entire project and finding patches for the bugs that we could patch. There's a little bit of ambiguity here because, of course, as a static analysis technique, there are false positives. Our bug fixing approach is not better than the underlying analysis, although that would be cool. We have observed kind of anecdotally that our patching approach appears to be less successful when it tries to fix a bug report that's a false positive. So this gives us some indication that we might be able actually to augment the static analysis with an attempt to patch and say, well, okay, if it looks like we can't succeed here, maybe we need to reason more deeply and figure out if this is a true bug report. Another kind of interesting thing we've seen here is that there are bugs in these programs that are basically illuminated or can only be found by the static analysis when previous bugs in the same module have been patched. So this suggests another avenue that static analysis can be improved with automatic fixing. If you fix a bug that previously caused the analysis to abort, you can then move further and deeper into the code that you're analyzing than you could without trying to do the patching. So in addition to giving us an end-to-end system for automatic bug finding and fixing of certain classes of defects, we think there's a lot of room in the coming year to explore the possibility of improving analysis by using automatic program transformation in this way. But we're still looking into it, so I don't have initial results. Here's the first Git pull request we got accepted, and I'm proud of it, so I'm showing it to you. Actually, I'm also proud of the student whose profile picture is there, so I want to give a lot of credit to Renard Van Tonder, who's really done the bulk of this work. So if any of it sounds interesting, assume that the interesting bits come from him, because he's a PhD student, so he's the one putting in the long hours, right? So I want to conclude a little bit with the vision, I think that Will suggested, and hopefully I elaborated on. There are certain classes of bugs, many classes of bugs that share common properties that we can use to automatically find and automatically fix them across a variety of projects, often by reasoning semantically about what the code should do and abstracting away syntactic details. And the vision here is to have this end-to-end system where we can reduce the amount of time the developer has to spend thinking about these kinds of bugs that are relatively straightforward to patch automatically. And hopefully provide a suite of tools, I think, that are as natural and push button to use for a developer as a continuous integration testing rig or even a compiler. So even if we don't want to fix at compilation time, I think I would love for these tools to end up in the hands of developers who use them just as naturally as they do their compiler to find and fix certain classes of errors. And while we're not quite there yet, I think we're getting a lot closer. So happy to talk about this and anything else. But that is my conclusion. I think we have a few minutes for questions, or whoever's coming after can come up and let the pregnant lady sit. You don't have to hide.
Thank you. This is actually really cool. I had a quick question. When you do insert your repairs, how sure are you that you're not introducing another path of a vulnerability, for example?
So if I can rephrase the question to make sure I'm hearing it, and I assume it was directed at me, although I can't tell because these lights are super bright. when we insert a patch, how do we know that we haven't inserted bad behavior? say,
Right,
Or
right.
another patch that would lead to bad behavior. So in the case of the static work I'm telling you about, we can really lean really heavily on the fact that we're using a static analysis that reasons exactly about the kinds of memory or safety problems that we could possibly introduce by introducing like memory manipulating constructs. And so there's a pass at the end that I didn't really talk about where we just run the analyzer
okay.
again.
You-
And so
you-
if it's happy, you know. And so I don't want to say that there's no circumstance in which something weird could happen, but we have seen the analyzer catch weirdness. And so we have as much confidence in the correctness of the program as you would having run the static analysis tool in the first place if it didn't.
I'm just curious, have you folks tried something like automatic exploit generation or the AEG tool just to sort of address that problem where you repair a program, run AEG to figure out if there are any outstanding exploits or paths that could be exploited?
So we haven't done that for this kind of work. We do have a body of work in test-driven automatic program repair where instead of finding a bug using a static analysis, we take a failing test case and attempt to cause it to pass by making a source level patch. And the risk there is actually much higher, I think, than for the static tool because we don't have the static tool there. We have done case studies into the kind of thing you're suggesting, which is to say try and use like fuzz testing or exploit generation based on the original exploitative input to make sure that we address the actual underlying cause and not just a symptom of a bug.
Right.
That isn't a guarantee on any particular technique, but we have done it for particular patches generated for particular techniques in particular use cases. And sometimes it works and sometimes it doesn't. But this is actually a big driving force in modern research on program repair, is how can we have confidence in the quality of the patches. So we have a bunch of different avenues, I think, to tackle that, but I don't think it's a solved problem yet.
All right, thanks.
I'm not trying
So,
to dominate the world,
could be old school here, but some of the techniques that have been most effective historically are techniques that discover errors that were not in the code at all. And some of the best ways to find errors that are not in the code at all is to begin by sitting down with prospective users and anticipate what might be the worst possible error that could be found in this code or in this system that's being built, and then progressively getting from the most complex, most important, most critical error, which might not be in the code at all. It might be code that's left out of the system or application instead of code that's actually in there. How do you go about addressing that class of error? And then the other technique that has been most helpful historically is actually code reading, so that human beings go through the code, read it, understand it, and discover types of errors that are at least extraordinarily difficult to discover by any kind of external analysis tool, I believe.
What do you want? Okay. All right. So I have a sort of multi-layered question. So the first question about effectively missing code or code that should be inserted to address a possible mistake. I don't think that the techniques, and Will can jump in and defend himself, I don't think the techniques we're talking about today are going to be particularly well suited to those kinds of errors, and I'm actually okay with that. In the sense that I think we're going to need, in the same way that we need a sort of multiplicity of assurance techniques to find and deal with the wide variety of mistakes that humans can make in implementing systems, I think we need a multiplicity of techniques to automatically address them. So in that respect, a static analysis tool, which I often think of and sort of teach as automated code review tool, they're good at finding certain classes of errors, and I think they will be good at guiding the repair of certain classes of errors by taking advantage, like we said, of the properties they have in common. I don't see them being especially good at finding these kinds of very custom issues that you really need to talk to a user about, which isn't to say that there isn't hope for that kind of issue. In fact, I think some of the test case-driven stuff that can maybe help define in a test-driven development way a desired feature could ultimately, not today, help guide, maybe in an interactive way, the synthesis of missing code in a way in which we'd have more confidence. So I think that that is plausible in sort of a future direction sense of helping develop code that's missing. I don't think that the techniques we've presented today are going to be perfectly well suited for those, but fortunately there are so many different kinds of bugs in the world that, we've got room for a lot of different techniques. The second question is about code review. I agree that code review is still one of the best ways to find mistakes. I think that code review, and this is just me speaking off the cuff, would be time better spent if developers didn't have to figure out integer overflow vulnerabilities or missing or missing like file handle releases on corner cases, right? Like humans can find that, but we know that code review sessions need to be time constrained and time boxed for them to be effective. And I'd rather developers be able to spend that time thinking about the deeper stuff the tools can't find than chasing down memory leaks that tools can find and fix, right? Like, to me, it's a question of effective use of developer time. And so I think this kind of technique can allow developers to use their code review time more effectively because they're not chasing down the kinds of things that tools can deal with for them.
I didn't mean to suggest that what you're doing is not important.
Oh, no,
Just that there's other important stuff that's not included at all.
absolutely. I completely agree with you.
All right, so the question is, this looks at finding potential fixes in the, I guess, elsewhere in the same code base,
Yep.
right? So if you can't find a potential fix elsewhere in the same code base, do you then go to some other repository to try to find potential fixes for similar problems?
So we have, in this particular project, we have done two kinds of searches. One is local actually to the module in which the bug is found. And then if we don't find a patch there, looking globally over the whole project. So this isn't quite what you're asking. You're asking, okay, if we can't find anything in the same project, do we look at all of GitHub, for example? But what we've noticed actually is that if we can't find it in the same module, adding the whole project actually doesn't seem to add very much, which I thought was kind of interesting. I expected it to. I would love to go to GitHub actually because there is a lot of evidence that code is very patterned and redundant. And so if you forgot to deal with your memory appropriately in your project, somebody probably did it properly elsewhere. The issue there is just scale. And so I think we need to develop better kind of indexing and searching and sort of honestly database management strategies to help do that kind of search effectively before we can really do it in a scalable way. What we've noticed though is that looking fairly locally, and that's consistent with other results in empirical software engineering, is actually really effective in finding repairs for the kinds of mistakes we're finding, which I find both encouraging and discouraging in equal parts.
In that case, thank you so much.
Thank you.